Okay, the purpose of this podcast is to show the derivation of both vector and Cartesian forms of an equation of a plane. Let's start off and show the derivation of the formula using a specific plane with individual specific coordinates, and then after that show the generalization of the formula um, in both vector and Cartesian form. And so what I'm going to do is I'm going to begin with a point, and in this particular case my point will have coordinates 1, 2, and 3. Keep in mind a point is also referred to as a position vector, and a position vector has no dimensions in the sense that it has no length, no depth, and no width. We're now going to take that point and move into the realm of one dimension, namely in the form of a vector equation of a line. Vector equations of lines can be represented using xyz. xyz would be the general point on the line, and the general point on the line really represents any and all points along that line. In this case we're working with a specific line, and that line will have as one of its points the position vector, or the point 1, 2, 3. And then what we're going to do is add in a parameter t and give the line a direction. In this particular case we'll use the direction 1, 2, minus 3, and what we have in this particular case is a vector equation of a line in space, and in this case what we've done is we've added a dimension in the sense that lines will have length, no depth, and no height. What we're going to do now is, following the exact same logic, the idea of defining a plane is that it is a representation of all possible points within a specific plane. And once again, if we consider a line to be the collection of an infinite number of points that travel in a particular direction, then we must look at a plane as a collection of an infinite number of lines that travel in many directions within the plane. And so in this particular case I'm going to incorporate the equation of the line, or rather the line from above, and that's why I am using the same position vector and the same direction vector. And really all I'm going to need to do in this particular case is add a second direction, and that second direction will have a different parameter. And what's important for the second direction is that this direction must not be parallel. And if you consider the idea that a plane is represents, or rather the equation represents all of the points in the plane, then we must be able to navigate to any point contained within the plane. And if we have direction vectors which are scalar multiples of each other, this means we can only move along a line and we cannot move within the plane itself. And so in this particular case I'm going to use a direction vector of 5, minus 1, minus 1. This is a vector representation of an equation of a plane, and what I'm going to do now is show you what this looks like using autograph. And so I'm going to open up Autograph. I'm going to open up a set of 3D axes, and so we've got length, width, depth, or length, width, height, either way you want to look at it. I'll just change the background, and what you can see here is a bounding box. The bounding box really is just to help you visually. We don't need the bounding box. What I am going to do, however, is just edit the axes to make sure that any graphing that I do will include or show all of the relevant pieces. And so I'm going to set my boundaries at -10 and 10 for all 3 of the axes. Okay, and so visually that will make no difference. And then what we're going to do is begin by building, as I did in the notebook, with coordinates of a point first, and I will use the same point that I used before. And what we're going to see over there is the point appearing in space, so to speak. The coordinates allow me to navigate from the origin to this specific point. I'm also able then to build on this point and add a dimension to it, and what I'm going to do is incorporate that same point, which would be the point 1, 2, 3, into the line. And my line in this case is going to have the same direction vector as I gave the line in the notebook. And so it has its position vector over here, and it has its direction vector 1, 2, -3. And what you'll find is that what we get now is an equation of a line, or rather we get a line with the specified direction passing through the given point. And if I rotate the axes, we can get different views of that line from different vantage points. Okay, and I'll just reset the orientation again to go back to where we were at the beginning. And now the theory is I'm going to take this line, and in order to have an equation of a plane, I need to be able to navigate to any point contained within the plane, and in order to do that I need a second direction vector, as I mentioned before. And so what I'm going to do is show you a representation of the line. I'm going to create a vector line which uses the same point as we started with, and the second direction vector. And so in this particular case, once again, I'm going to select the point 1, 2, 3, and this time I will use the second direction vector and what we're going to see over there is we've got 2 lines, and those 2 lines, depending on which view I take, you can see share a point and therefore obviously intersect. And from a side view, if you will, you can see that those 2 lines can be contained within a plane, and that in fact a plane can consist of an infinite number of lines in an infinite number of different directions. But what we don't want to do is add another dimension to those and move into space, and so we want to keep it as length and width, or vice versa. And so what we're going to do now is enter an equation of a plane which incorporates those 2 directions or lines and therefore also includes the point. And so this time I'm going to use the same point. The direction vectors I'm going to use will be the 2 direction vectors from the line, or rather from the 2 lines. And what we're going to have now is an equation of a plane, or rather a representation of a plane. And if we look from the side view, what should hopefully be obvious is that that plane contains those 2 lines, and we are now in a position to navigate anywhere within this plane using my starting point and my two direction vectors with their respective parameters. Now, the downside or the limitation of a vector equation, or rather an equation of a plane in vector form, is that it isn't particularly user-friendly. And so what we're going to do now is take this vector equation of a plane and we're going to put it into another form. And so what we have over here is our vector equation, and hopefully it's fairly obvious that what we're representing is two dimensions, length and width, just as we would in a regular coordinate plane or Cartesian plane. And so what we're going to do first and foremost is, if we go back and have a look at our plane, what you will hopefully see is that it is possible, instead of having the two directions, to represent the plane using something called a normal. And what we're going to do is we're going to go back over here. I'm going to take the two direction vectors and I'm going to evaluate the cross product of those two direction vectors. Okay, and if we evaluate the cross product of those two, alright, and I'm just going to use multiplying down and adding, and then multiplying up and subtracting. What I'm going to obtain is minus 2i, I times 2 times the minus 1, minus 15j, minus k, minus, and then multiplying up, 10k plus 3i minus j, and I'm going to add and subtract my like terms, and I'm going to write it in vector form. I'm going to obtain minus 5, minus 14, and minus 11. And what I've obtained there is a vector which is perpendicular to both of the direction vectors that I selected for my plane. And what we do is we refer to this vector as the normal to the plane. Okay, and so what I'll do now is show you what the or how the normal would appear in this particular case. And so what I'm going to do is select my point, and I'm going to select the plane, and I'm going to have the autograph software show me a representation of the normal. And what should hopefully be obvious from this is that that line, or that vector, is perpendicular to both of the lines within the plane, and in fact is perpendicular to the plane at all points contained within that plane. And the normal is key to the derivation of the Cartesian form of the equation of a plane. And so what we'll do is go back to the notebook, extend the page to give myself a little more space, and what we're going to do at this point is I'm going to take the vector equation of the plane and I'm going to multiply through by the normal that I obtained below. Okay, and so I'm going to go back in over there, and so what I'm looking to do at this point is to take the equation of my plane, in vector form and I'm going to multiply the entire equation by the normal, which effectively means I'm going to find dot product of the normal times each of those, and same thing on the left hand side of the equation, a dot product of the left hand side as well. And so what I'm going to be left with is, on the left hand side of the equation, I will have x, y, and z, which represent all points in the plane, and I will find the dot scalar or inner product using -5, -14, -11, which is the direction vector of the normal of the plane. I'm going to do the same thing over here. And hopefully what you realize at this point is that when I find the product of, or rather the dot product of the normal and the first direction vector, that what I'm going to be obtaining is 0, and likewise I will obtain 0 for the second dot product. The reason for that, of course, is that the vectors are perpendicular to each other, and the dot product of perpendicular vectors is in fact 0. And so my equation at this point is now going to be significantly simpler, and I'm going to be left with, after a little bit of simplifying, -5x -14y -11z, which is equal to, in this particular case, -5 -28 -33, and I'll just write that out one more time. And what we've obtained here is the Cartesian form of the equation of our plane. As you can see, it's a much simpler form of the equation to work with. And what's important to note is a couple of the key elements. This is referred to as D in the notation, and these are A, B, and C. And that relates to the general form of the equation of the plane, which is written ax plus by plus cz equals d, and that is a Cartesian form of an equation of a plane. D, of course, is a scalar value and is obtained by finding the dot product of any point within the plane and the plane's normal. Okay. This shows the specific derivation of the two different forms of the equation of a plane. Firstly, we see our vector form and the much more user-friendly Cartesian form of the equation of a plane. And that is it.